Assalamualaikum everyone. Welcome back to Sir K Loves Physics and Chemistry tutorial for high school students. Today's episode is a revised excerpt of a past upload focusing on solving problems that involve self-inductance. So stick around till the end of the presentation. Watch and learn. From the law of electromagnetic induction, we say that a changing current passing through the coil can induce a magnetic field and hence a magnetic flux in the coil. This changing flux also induces an EMF. And the property of the current carrying coil to oppose the change in current is what we call self-inductance of the coil. And we denote self-inductance or simply inductance by capital letter L, all right, which is determined by multiplying the number of turns in the coil by the average magnetic flux denoted by the Greek letter phi or P sub B to be divided by the current small letter I. So we emphasize the meaning of each quantity in this equation. Capital N, again, is the number of turns in the coil. The Greek letter P sub B refers to the average flux due to current through each turn of the coil. And small letter I is the changing current passing through the coil. And the induced EMF or electromotive force denoted by the Greek letter epsilon is just equal to negative capital L, which refers to the inductance, multiplied by the changing current delta I divided by delta T. All right. Each of these quantity is also emphasized. So epsilon means the self-induced EMF in the coil or in the circuit. Capital L is the inductance of the coil or the circuit, and the ratio delta I over delta T refers to the rate of change of current in the circuit. All right. So this formula implies that the greater the inductance, capital L, the larger is the induced EMF. And also, the faster the current in the coil changes, the larger is the induced EMF as well. Now, the negative sign is simply to emphasize Lenz's law, which states that the direction of the EMF induced in the coil by a changing magnetic flux is such that the magnetic field created by the changing current opposes, so that's the key word, opposes the changes in the initial magnetic field. A long straight solenoid has 800 turns. When the current in the solenoid is 2.90 amperes, the average flux through each turn of the solenoid is 3.25 times 10 to the negative 3 Weber. Question: what must be the magnitude of the rate of change of the current in order for self-induced EMF to equal 6.20 millivolts? Alright, so in answering this question, we first calculate for the self-inductance, capital L, using this formula. Okay, capital L is equal to
the number of turns in the coil multiplied by the average magnetic flux, denoted here by the Greek letter P sub B, and divided by the current I. And then, after getting the self-inductance, capital L, we can already use the formula for the rate of change in the current, delta I over delta T, simply by dividing the self-induced EMF, or epsilon, divided by the self-inductance, capital L. Alright, so using the formula for self-inductance, capital L, which is equal to capital N, Greek letter phi sub B, which represents the average magnetic flux induced in the coil, with to be divided by the amount of uh, the changing current I. Substituting 800 turns multiplied by the amount of average magnetic flux, 3.25 times 10 to the negative 3 Weber, and divided by 2.90 amperes. Doing our math, we will get the value for self-inductance, capital L, equal to 0.897 Henry. Alright? So, using the formula for the rate of change in the current, delta I over delta T, which is just equal to the amount of self-induced EMF divided by the amount of self-inductance, capital L, and substituting the given EMF, 6.20 millivolts, or in volts, that's 6.20 times 10 to the negative 3 volts, and divided by the amount of self-inductance, 0.897. Instead of Henry, we change it to Weber per ampere, right? And simplifying, we will get the rate of change in the current being equal to 6.91 times 10 to the negative 3 amperes per second. So that is the rate of change in the current that induces the amount of uh, EMF given here, and the self-inductance that's also given here, 0.897 Henry. Note that how we were able to come up with the unit of the rate of change in the current as ampere per second, because Weber can also be expressed as 1 volt second, right? So if you substitute, instead of Weber, we have 1 volt, or 0.897 volt second. Eventually, the unit volt cancels out, and we are left with ampere per second as the final unit of our answer. Question number 2. A solenoid 25.0 centimeters long and with a cross-sectional area of 0.500 centimeter squared contains 400 turns of wire and carries a current of 80.0 amperes. Calculate, letter A, the magnetic field in the solenoid. Letter B, the energy density in the magnetic field if the solenoid is filled with air. Letter C, the inductance of the solenoid. Letter D, the total energy contained in the coil's magnetic field, assuming that the field is uniform.
For our solution, starting with question letter A, finding the magnetic field capital B in the solenoid, all right? This is determined by just multiplying the permeability of free space denoted by mu naught, that is to be multiplied by the current small letter I, and the number of turns per unit length, all right? So substituting, we have the value of the permeability of free space equal to 4 pi times 10 to the negative 7 Weber per ampere meter, all right? So that will be multiplied by the current 80.0 amperes and the number of turns, all right, 400, all right, per unit length. This is the length of the solenoid, 0.250 meters. So doing our math, we will get the magnetic field, all right, inside the solenoid capital B equal to 1.61 times 10 to the negative 1 Tesla. And for question letter B, we are asked to find the energy density denoted by small letter U. This is the energy density, all right, in the magnetic field if the solenoid is filled with air. And the formula for energy density is just the square of the magnetic field, or capital B squared, divided by twice the relative permeability of the material. In this case, air is the material inside the solenoid, all right? And this relative permeability, mu, is just equal to a constant, K, which is a unitless constant equal to 1, all right, for air. And that will be multiplied by the value of the permeability of free space, mu naught, 4 pi times 10 to the negative 7 Weber per ampere meter. So plugging in the data to this formula, we have, all right, the energy density U is equal to 1.61 times 10 to the negative 1 Tesla. That will be squared and then divided by twice the relative permeability, or that will be 8 pi times 10 to the negative 7 Tesla meter per ampere is just the same as Weber per ampere meter. So again, doing our math, we will get the energy density, small letter u, equal to 1.03 times 10 to the fourth power Tesla ampere per meter. All right? So this unit, Tesla ampere per meter, is also the same as joules per meter cube. So our answer to question letter B is that the energy density is equal to 1.03 times 10 to the fourth power joules per meter cube. Moving on to question letter C, where we're asked to compute the inductance, capital L, in the solenoid. So the formula is capital L equals the number of turns in the coil, capital N, times the magnetic flux, P sub B, and divided by the current, small letter I, where the magnetic flux, P sub B, is equal to the product of the magnetic field, capital B,
and the cross-sectional area of the solenoid. So, plugging in the data into this formula, we get 400 multiplied by 1.61 times 10 to the negative 1 Tesla, okay, times 5.00 raised to the negative 5 power meter squared all over 80.0 amperes. So when we do our math, we will get the value of the inductance, capital L, equal to 4.03 raised to the negative 5 Henry. And lastly, we also find the total energy, capital U, contained in the coil's magnetic field, assuming that this field is uniform. So, using this formula, total energy, capital U, is equal to 1/2 the product of the inductance, capital L, and the square of the current, or I squared. Alright? So, substituting the data, we get 1/2 multiplied by 4.03 times 10 to the negative 5 Henry multiplied by the square of the current 80.0 amperes. So that's to be squared. And finally, all right, simplifying this, we arrive at the value of the total energy, capital U, equals 0.129 joules, rounded to 3 significant figures. So that's it. We are done. Till the next episode, mabuhay, mashallah. Thank you very much for watching. Please follow me in my FB page, and please don't forget to subscribe to my YouTube channel.